Hello everyone. Today I'll be discussing how to generate the shear force and bending moment diagram for the beam loaded as shown in the figure. The first step will be to find the reactions and as we can see the cantilever beam is free at one end and fixed at the other. So there will be three components of the reaction at the fixed end, namely RAX, RAY and MA. Now, to find these three reactions, we can apply the equilibrium equation sigma fx is equal to 0, sigma fy is equal to 0, and sigma ma, the moment about point A, is equal to 0. But as the beam is free at the other end, this step can be omitted. And this is a general practice is that whenever we are finding the shear force and bending moment diagram of a cantilever, we will always start with the free end and omit the step of finding the reactions. So to generate the shear force and bending moment function, first of all, we have to see the load distribution. Now we can see in this problem that the uniformly varying load is first increasing at a constant rate up till the 12-meter mark, and after that it is decreasing at a constant rate. So this beam will have two separate shear force and moment functions. One will be applicable for the region from 0 to 12 meter, and the other one will be applicable from 12 meter to 24 meter. So first of all, we will generate the shear and moment function for x is equal to 0 to 12 meter from the right section. So we will split the beam at an arbitrary distance x into two halves. And once the beam is split into two halves, we can see as the beam overall is in equilibrium. So both the halves should be independently in static equilibrium. Now, if we concentrate on the right segment, now the equilibrium free body diagram of the right segment is shown here. We can see that there is a uniformly varying load acting on the right segment. And now this uniformly varying load will generate a total downward force as well as a moment. And to counter this moment, the left segment is exerting internal forces on the right segment, and due to these internal forces, the shear force applied by the left segment on the right segment will be V, will counter the total downward load, and the moment M exerted by the left segment on the right segment will counter the total moment generated by the uniformly varying load acting on the right segment. Similarly, the right segment will apply equal and opposite reactions on the left segment as shown in the figure. So now we will generate the shear and moment function for x such that x lies between 0 and 12 meter. So here I have shown the region of x is equal to 0 to 12. So now we have magnified this segment to the right of this section AA, and this is the free body diagram of this section. Now here we can see that there is a uniformly varying load that is increasing from 0 to W. W is the uniformly varying load acting at a distance x. So to find this load intensity W at a distance x, we can notice the similarity between these two triangles. One is of the height 4 and width, base width 12, and other is of the height W and base width x. So applying the similarity condition on these two triangles, W can be found using this relation, and it comes equal to x by 3. The total vertical load acting downward will be equal to the area of this triangle, and that has been calculated here applying the formula for area of triangle. Now this total load P will act through the centroid of the triangle, or we can say that this uniformly varying load can be replaced by a concentrated load P that is equal to area of this triangle and acting through the centroid of this triangle, and the centroid will be at a distance of x by 3 from the left end of the triangle and 2x by 3 from the right end of triangle, as the width of the triangle is x. Now once we have generated this equivalent free body diagram, then we can apply the equilibrium equation sigma Fy is equal to 0 and sigma m is equal to 0. Now when we apply sigma Fy is equal to 0, what we get is V is equal to 1 by 6x square. The variation of shear force from x is equal to 0 to 12 will be given by this relation. Similarly, when we apply the moment equilibrium equation about this section AA, this is the equation that we get, and upon solving we get m is equal to minus x cube by 18, and this equation is also valid for x is equal to 0 to 12. So now the next step is we will go to the other segment, that is from x is equal to x is varying from 12 to 24 as shown in the figure. So again I have split it into two half segments at the arbitrary distance AA, and then the right segment is shown magnified here. So now we want to find the shear and moment function for this segment. So here the uniformly varying load acting in the green region can be represented by a concentrated force P as shown in the figure. Now this concentrated force P will act through the centroid of this triangle in the green region, and its magnitude will be equal to area of this triangle. And that has been calculated here, and also the line of action passes through the centroid, and the centroid will lie at a distance of 4 meters from the left end of triangle and 8 meters from the right end of triangle. So now the problem reduces to this. Now again we can see that this trapezoidal area in this figure is having a load distribution that is varying from 4 Newton per meter to W Newton per meter at the section X. So first step now will be to calculate this load intensity W at a distance X. So for this also we will apply the similarity condition between these two triangle, one the highlighted in red and the other the white region. So applying the similarity condition, we get this W by 4, the load intensity at the peak will be equal to x 24 minus x divided by 12. So upon solving, the load intensity at arbitrary distance x comes equal to the relation as shown. So now we have found the load intensity W. Now once we have found the load intensity W, the uniformly varying load as shown in this figure can be replaced by a single force P equivalent that is having magnitude equal to the area of this trapezium and acting vertically downward through the centroid of this trapezium as shown. And P equivalent will be equal to area of trapezium, and it can be found by using the relation as shown and then finally replacing the W as calculated previously. So once we have found P equivalent, the next step will be to find the centroid of the trapezium to locate the line of action of P equivalent. As the P equivalent calculated in previous section will act through the centroid. So here in this figure, we can see that the trapezium can be subdivided into a rectangle as well as a triangle. And the centroid of the rectangle will lie at the midpoint, that is at a distance of x minus 12 by 2 from the right edge as well as the left edge. And the centroid of the triangle will lie at a distance x minus 12 by 3 from the right edge. And the centroid will be D1 and D2 respectively. Now we know the coordinates of centroid C1 and C2 and the area of the triangle and rectangle. Then we can find the centroid of this trapezium by applying this formula. D is equal to A1 D1 plus A2 D2 by A1 plus D2, where A1 is the area of triangle and A2 is the area of, sorry, A1 is the area of rectangle and A2 is the area of triangle. That has been calculated here. So substituting all these values in this relation, we can find the distance D of the centroid of this trapezium from this right edge. Now once we have found the distance D from the right edge, then this is the equivalent diagram of the load distribution for the x varying from 12 to 24. So as we have previously discussed, the triangular load was replaced by 24 Newton, and the P equivalent that was calculated in the previous slide will act through the distance d from the right edge of the trapezium. Now we will apply the equilibrium equations. Sigma Fy is equal to 0 first. Now we can see that there are three forces V, P equivalent and 24 Newton. So applying sigma Fy is equal to 0, we get V is equal given by this relation for x lying between 12 and 24 meters. Similarly, applying sigma M is equal to 0, we notice that the unknown moment M at an arbitrary distance x and the moment generated by P and the moment generated by 24 Newton has to be calculated. So it can be seen here minus M as it is clockwise minus P equivalent into the distance of P equivalent from the arbitrary section at arbitrary distance x will be equal to x minus d plus 12. So that is the distance of P equivalent from the right edge. And then minus 24 into x minus 8. As all the three are clockwise, so they will be taken negative. So from here we can calculate the moment at an arbitrary distance x varying from 12 to 24 by this relation. Finally, collecting all the shear force and moment functions, this is what we get. This is the first one is the relation for shear force varying from for x line between 0 to 12. The second one is the relation for shear force from x line between 12 to 24, and the moment relation are also shown accordingly. Once we have generated the functions, then we can plot the curves. So here I have shown the curves. The first one is the loading. The second one is the shear force diagram as plotted using MATLAB, and third one is the bending moment diagram plotted using the MATLAB. So finally we will study the diagrams. Here we can see the shear force is 0 at the right end and it is increasing and it is going maximum at the left end A where the beam is fixed, and the bending moment is 0 at the right end and it is decreasing and it is maximum at the point A. So if the beam fails, it will fail from at the point A. If obviously assuming if the beam is of uniform same material and uniform cross section. So that's all about generating the shear force and bending moment diagram. Thanks for joining.